Okay, our final problem today is going to be one with quenching. So we're going to have a container here now, a tank maybe. It's going to have water in it, and we're going to put some metal, something metal here in it to quench it. So here is going to be this metal is going to be initially, it's going to be 1 kilogram. It's going to be at a temperature initial of 1075 Kelvin. And we're going to say this substance has a specific heat of 0.5 kilojoules per kilogram Kelvin. And in this tank is going to be 100 kilograms of water. And its temperature initial is going to be at 295 Kelvin. And if we look that up, we can say that this specific heat is like 4.2. So we look at the C sub P, 4.2 kilojoules per kilogram Kelvin. Now you look at this problem, and we're gonna create our control volume is going to be the tank. And you can think of this problem, you say, well, it's metal. First of all, when we have a metal, it should, bells and whistles should go off in your head and say that's and even the information they gave to us in the problem, this is an incompressible substance type problem. Water can be incompressible substance because it's going to stay as a liquid in both states, state 1 and state 2. So it's but it's a closed system here. So we're going to look at this and we're going to say, well, we have the change in kinetic energy plus the change in potential energy plus the change in internal energy is equal to the heat transfer minus the work. Okay, now, no kinetic energy change, no potential energy change here in this tank. Not going to be moving it anywhere. And we can assume that if you have a big tank with 100 kilograms of water into it, there's not going to be a lot of heat that's leaving that tank. I mean, if you quench something in a big tank, it's not going to be leaving that tank. It's going to be the heat from the metal is going to be increasing the temperature of the water, but only very slightly. So we can assume it's basically an insulated tank. And there's going to be no work on that tank at all. There's not going to be anything that's going to be changing its volume or anything to be added into it, like a paddle wheel or anything like that. So we have delta U is equal to 0. Okay, so we're going to have the change in internal energy of my water plus the change in internal energy of my metal, because we can't just look at one thing. We have to look at, both things. They both have a different internal energy change, so we have to look at them separately. So summation of all the internal energies. And this is going to be mass of the water times U2 minus U1 of the water plus mass of the metal times U2 minus U1 of the metal is equal to 0. Now here's when we're going to do the incompressible substance model. And so I often say if you do the incompressible substance model for one thing, you're going to have to do it for both things. It's best practice to do that. Okay? And so we have mass of the water times specific heat of the water times T2 minus T1 of the water plus mass of the metal times the specific heat of the metal times T2 minus T1 of the metal is equal to 0. And we know that when this metal goes in there and quenches, it's going to reach equilibrium, and so the temperature too is going to be the same between these two, but the temperature initial is going to be different. Okay, and so we're going to get down here to basically 100 kilograms times 4.2 kilojoules per kilogram Kelvin times our temperature final minus our temperature initial, which is 295 Kelvin, plus we have that 1 kilogram part, so 1 kilogram times 0.5 kilojoules per kilogram Kelvin, T final minus our T initial there, which is 1075 equals 0. Okay, that's really all there is to this problem. It's not a very challenging mathematical problem. I want you to find out what TF is, of course. So I recognize this problem is going to be, that's the first law problem. I need to make it a second law problem. So this temperature final here is going to be equal to 295.9 Kelvin. So it's very close to 295. It doesn't change it appreciably at all. Okay. But now what we have to do is now I want to find out how much entropy is produced in this problem. So that's where I want to go. I was disregard what I said previously. We want to check this problem and say, okay, delta S is equal to the summation of the heat transfer, the temperature at which the heat transfer occurs, plus sigma. And we're going to say that there's no heat transfer here, so we're going to have the delta S of the water plus the delta S of the metal is equal to sigma. Right, here's where we're going to do the incompressible substance model for that S. S is what I want you to work on. So here is where we're going to say sigma is equal to the mass of the water times the specific heat of the water times the natural log of the temperature final over the temperature initial of the water plus the mass of the metal times the specific heat of the metal times the natural log times the temperature final over the temperature initial of the metal. This is what I want you to find. I want you to find sigma here. So sorry for all this nonsense. Please find sigma. That's what I want for your final question. I'll try to edit this so it makes some sense. All right. Through and make that incompressible substance model evaluation of this problem. That's really what the key or the trick is here. Right, and that's really all I have for you today. I want to do 3 problems that I work through with you. Challenges you in different ways. We have an ideal gas, we had an incompressible substance, we had a water which had a vapor dome. So if you were following along with these problems and thought these were pretty straightforward, then they should be okay. But the key thing is that you're going to have all these equations. How do I find the unknown for this equation? Do I use the second law to put it in the first law, or the first law to put it in the second law? Do I use ideal gas model to find a pressure? All those things have to be understood very, very well for this next exam. So please make sure you're doing that. So again, this is going to cover, the next exam is going to be, okay, I stopped the video instead of pausing the video, so let me make sure I get this. Transient material is on this exam. Okay, it's going to be chapter 4, the very end, transient material, all of chapter 5, maximum efficiencies, Carnot cycles, Clausius inequality, and then chapter 6, which you're talking about open and closed law, system, second law. That's what we're doing on this next exam. Make sure you understand those things. I'll make sure the study guide's updated so it reflects those things. But if you have any questions, let me know, and we'll go from there. Best of luck.